and these concepts will be treated as the graphical components. But before going into the details, let me first give you some intuitions on how these concepts can be inferred. First, at the dataset level, what concepts does the LM use to make predictions? To figure this out, we would first need to feed all the image patches from a dataset to a vision transformer, and then to get the corresponding visual encodings. And here, the concept is represented by a cluster of similar patches. For example, this is the concept of green leaves and weeds, and this is the concept of purple petal. So how do we really get these dataset level concepts? As I mentioned earlier, we need to first feed these patches into the vision transformer and get all of these patch embeddings, and then we can put these patches in the embedding space and try to group them into clusters so that each cluster can represent one concept. How about patch level? Specifically, we want to know which concept does each image patch belong to. This is fairly simple. For each image patch, we can simply cluster it or assign it to its nearest concept or cluster center. For example, we can assign this image patch to concept 1, and we can assign this image patch to concept 3. And similarly, at the image level, we want to know what concepts are activated for this image specifically. And our idea is for this image, we're going to count how many patches belong to each concept. For example, after counting, we can figure out that most concepts actually belong to concept 1. Most patches actually belong to concept 1 and concept 3. Therefore, from the dataset level concepts, we can get this image level concept explanations. However, there is a caveat here. Not all patches are equally important. For example, the background patches of green leaves and weeds, they're supposed to be less important than the foreground flower patches. And in this case, how can we adjust the count? Our idea is to just count the patches weighted by the attention which is already available in the transformer. And for example, we can count each background patches as 0.5 patch, and specifically for this background patch, we can count it as 0.5 patch in concept 1. And for this foreground flower patch, we can count it as 2 patches in concept 2, in concept 3. And similarly for this patch. This way, the background concept of green leaves and weeds is basically reduced to a smaller number, and the explanation would make more sense. Now, these are just high-level intuitions, but in practice, in order to robustly infer these concepts, we still need to treat these transformers as the deep component and all of these concepts as graphical components. And given these internal neural embeddings, the patch embeddings as observables, we need to formally infer these high-level concepts and use them as explanations. So formally, in our graphical model, we assume M images, and each image has J patches. This EMJ is the patch embedding for image M patch J. And each patch embedding will be weighted by its corresponding attention, AMJ. And the generative process will start with the dataset level concepts, and each concept will be represented using a cluster mean, mu u, and the covariance sigma k. And we have k concepts in total. At the image level, we're going to generate a concept string for each image M, indicating which concept is activated for this image. And after that, at the patch level for each patch, according to the image level concept string, we're going to sample one concept, ZMJ, to show that which concept this patch belongs to. So for example, in this image and in this patch, we're going to first choose concept 1 as ZMJ, and then we're going to generate this patch embedding from concept 1. And similarly, we can generate other patch embeddings from its corresponding concepts. So far, we have several key properties of our concept explainer. we have a multi-level explanation structure. Specifically, we can have the dataset level, image level, and patch level explanations. We also have a continuous patch or token count. For example, a patch with more attention, AMJ, will count as more than one patch. And in general, patch J counts as JA patches, where JA is a continuous number. However, even with these nice properties, we still have several remaining challenges. The first challenge is explanations. It may be irrelevant to the predictions because we're primarily focusing on the patch embeddings of the transformers, right? Therefore, it might not be really relevant to the prediction that we're trying to explain. Therefore, one corresponding additional property we want is the relevance to predictions. And to achieve relevance, we're going to first also treat the prediction from the multimodal LM ym hat as observed variables. And then we're going to assume that our concept explanations can produce these prediction using a linear model. And by doing this, we can make sure that the concept explanations are relevant to the model prediction. And the second challenge is too many concepts. It's too many, so many so that it's actually not very human-friendly or understandable. Therefore, we want sparsity of concepts. And the solution is actually quite simple. Under Bayesian framework, we only need to place a dirichlet prior distribution on the image level concept explanation to encourage sparsity. And by doing this, we can substantially reduce the number of activated concepts for each image to a substantially smaller number. And the third challenge is that the explanations may not be very stable, and it may change if the images are perturbed. For example, this is the original image, and the expander will say that this image is most relevant to concept 1 and concept 3. But if we corrupt the image by only changing its color, now the most relevant concept will suddenly becomes concept 4, which is wrong. And correspondingly, another desirable property we want is the stability of explanations. And ideally, for both the original image and the corrupted image, we would want their explanations to be identical. So both should be concept 1 and 3. So to achieve stability, given the original image and its corresponding concept explanation, we're going to generate a corrupted image and its corresponding concept explanations at MJ prime. And then we're going to push them together using the self-supervised label YS. So this YS indicates whether image M and M prime are from the same image. So this is basically a constructive learning mechanism to push image M and its corrupted version together in the concept space. So for concepts from the same image, we're going to push them closer, and for concepts from different images, we're going to push them farther away. This way, we can have a Bayesian deep learning explainer with nice properties, including relevance, sparsity, and stability. And note that in our framework and in this Bayesian deep learning explainer, the process of concept inference is actually the process of interpretation. So given these observed token embeddings from population models and model predictions, we're going to infer the dataset level concepts, image level concepts, and patch level concepts, and we're going to use them as explanations or interpretations. And so here, note that we have been talking about the explanation of the vision transformer only, but similar techniques can actually be used to interpret the language transformer as well. Only that the different level, the meaning of different level would change. For example, the image level would become document level or question level. And in terms of theoretical analysis, obviously inferring these concepts can be done by maximizing the evidence lower bound or elbow of the LM token embeddings. And we can actually show that this elbow is upper bounded by 3 terms. The first term is the mutual information between LM token embeddings and the concept explanations. And maximizing this term would ensure that the explanations are relevant to the LM. The second term is the mutual information between the prediction YM hat and the concept explanations. And maximizing this term would make sure that the explanations are relevant to the prediction. The third term would be the mutual information between the concepts from the original image M and the concepts from the corrupted image M prime. So these two are a pair of images, and maximizing this term will make sure that the explanations are stable against perturbation. In summary, maximizing the elbow is then equivalent to inferring relevant, stable concepts that interpret the foundation model. To see how well our method really works, let's start with a toy dataset we constructed with two classes. And here, images of class 0 contain yellow and red patches, and images of class 1 contain blue and green patches. So in total, we have 4 latent concepts: yellow, red, blue, and green. And these are the dataset level concepts generated by our Bayesian deep learning explainer. We can see that it can actually successfully discover all of these 4 concepts. And given an input image, we're able to generate image level explanations and says that this image is actually most relevant to concept 3 and 4. And at the patch level, we will be able to recognize which concept each patch belongs to. And similarly, for another input image, we can generate its corresponding 3-level explanations. Besides the toy dataset, we also evaluate our method on real-world data. For example, the Oxford flower dataset, which contains over 100 categories of flowers. And these are the dataset level concepts generated by our explainer. We can see that similarly, it can also successfully discover different concepts. For example, this is the concept of green leaves and weeds, and this is the concept of purple petal. And given an input image, we will be able to generate image level explanations and says that this image is most relevant to concept 1 and 3. And similarly, at the patch level, we will be able to tell which concept each image patch belongs to. And for another input image, we will be able to generate the corresponding 3-level explanations. And just to summarize for this part, we developed the first general framework for concept-based interpretation for multimodal LLMs, and we formulate in the process of interpretation as probabilistic inference, and our explainer can generate human understandable interpretation with relevance, sparsity, and stability, and it also offers new opportunities for controlling LLMs. Now that we have talked about the Bayesian deep learning framework in the context of language and vision, let's move on to see how it can be useful in network analysis. So the problem setting here is that we have a black box graph classification model, for example, a graph neural network, and this model will take in a graph and the node content for each node in the graph to predict a label. For example, take in one molecule graph and to predict whether this is a poisonous molecule or not. And our goal is to generate a subgraph as the causal explanations for the prediction. And our solution would be a Bayesian deep learning based causal explainer to generate subgraphs as causal explanations. And in here, the deep component would be the graph classification model with the node content and graphs as input. And the graphical component would handle the causal relations among the node content, latent factors, and the network of the graph. Essentially, it acts as a causal explainer for the black box model. But before going into detail, let me first give you a very high-level introduction of causal relations using the famous ice cream example that analyzes whether ice cream causes more drowning accident. Now, let's say that X is ice cream sales, and variable Y is the number of drowning accidents. And if we plot the number of drowning accidents versus ice cream sales, we can see that maybe ice cream does cause drowning accidents, and perhaps the government should ban ice cream altogether. But if you look closer, you might find that there is actually a third variable, season, as a confounder. And specifically, when the season is summer, more people will be on the beach and there will be more ice cream sales and there will be more drowning accidents. And if the season is winter, there will be fewer people on the beach and therefore fewer ice cream sales and fewer drowning accidents. So in this case, season is the cause here, not the ice cream. And we're getting this contradiction because we're using and we're measuring conditional relations. And when we're measuring conditional relations, the dependency will flow from the ice cream cells through the confounder season to the number of joining accidents. Therefore, we can see that conditional relations sometimes can be misleading. We need causal relations. So to obtain causal relations, we need to first cut the link between the ice cream cells and the confounder. And then this way, the dependency can flow directly from the ice cream cells to the number of joining accidents. And in causal inference, we call this the do operator. And after correcting for this, we can see that there's actually no correlations from the ice cream to joining accidents. And we can actually follow the same procedure to build a Bayesian deep learning explainer to generate subgraph as causal explanations for black box graph classification model. And specifically, we can use the graphical component to model the relations between the input graph, the node content, the causal latent factors and the spurious latent factors, and then we can remove the confounders to generate the subgraphs as the causal explanations. Here, the deep component would be the black box graph classification model, and the graphical component would be our causal network. To see how our method really works, let's take a look at an example molecule graph. And in this graph, the original graph classification model predict that there's a 99 probability that this is poisonous. And given this graph, these are the generated subgraph from some baselines. And we can see that these explanations, the predictions are actually close to the region's prediction, which is good. However, these subgraphs actually contain a lot of fragmented edges. Therefore, they're not very meaningful subgraphs. And this is a subgraph generated by another baseline. We can see that this is a much more meaningful subgraph. However, the prediction it produces is wrong compared to the original prediction it's trying to explain. In contrast, this is the subgraph that's generated by our method. And we can see that our Bayesian deep learning-based causal explainers can provide both meaningful subgraphs and faithful predictions. And now that we have discussed how Bayesian deep learning can be useful in network analysis and graph learning, let's turn our attention to the third application, healthcare, to see how it can be useful. And here we're interested in a healthcare application called medication self-administration, or MSA. And in MSA, a patient need to go through a sequence of multiple steps to perform some action and administer the medication. For example, a diabetes patient need to use the insulin pen and go through a sequence of 8 steps to inject insulin. And an asthma patient may need to use the inhaler to go through a sequence of 6 steps to administer the corresponding medication. Now, the question we ask is, using an AI-based wireless sensor, can we automatically detect, has the patient taken the medicine today? Did the patient correctly perform all the steps, and what steps of the process needs to be improved and how? Essentially, we would try to answer the question that given the wireless signal, can we predict the starting time and ending time for each step? And in order to do this in a robust and interpretable way, we need to incorporate some domain knowledge from the clinicians. And the first domain knowledge we would like to incorporate is that different steps in the process actually has different duration distributions. For example, step 6 is administer the medicine and hold for 10 seconds. Since it's 10 seconds, it's relatively long duration, and therefore it has a larger variance. And in another example, in step 2, it's load cartridge. It takes only a very short time. Therefore, the duration is relatively short with a smaller variance. But obviously, it would be helpful to incorporate these distributions as prior distribution or domain knowledge into our model. The second domain knowledge we would like to incorporate is that the transition probability between different steps are actually different. For example, clinicians find that patients tend to forget step 2 after step 1. And therefore, there is a 50% chance that the patients, after finishing step 1, he or she will directly skip step 2 and goes to step 3. And obviously, we can incorporate these kind of transition probabilities into our model to improve robustness and interpretability. And to give you slightly more detail, this would be a dynamic Bayesian network combined with the deep learning component. So basically, our solution would be a Bayesian deep learning-based health monitoring model where the deep component handles the high-dimensional wireless signals, and the graphical component would be incorporating domain knowledge and make interpretable predictions. And these are the overview of our model. We have a deep component and the graphical component. The deep component consists of two stages. Stage 1 localizes and focuses on each person, and stage 2 will estimate the probability of each MSA step for each frame. Note that each MSA step, it actually contains multiple frames. And the graphical component would try to combine the estimate from the deep component and the domain knowledge to make the final prediction. And these are some of the results for our method. We can see that it actually performs surprisingly well, even in the case of out-of-distribution data, including missing step and short duration that have never happened in the training data. And this is how our methods can be integrated into a care management system. We start with the AI-based wireless sensor, which make the prediction, and it's gonna upload the predictions to the cloud. And a health professional, for example, a clinician, can use the predictions in the cloud and help the patients to improve its technique. And in addition, the cloud can also automatically send the reminders to the patients to improve his technique, to improve his or her techniques as well, in the cases where the patients forgot to take the medicine or performing some steps incorrectly. So you can see that Bayesian deep learning can improve both performance and interpretability. And so far, we have been talking about different concrete models under the framework, and know that for each model, we can actually have different parameter learning scheme. For example, we can have MAP to learn the point estimate of the parameters. We can also have a Bayesian treatment to learn the distributions of the parameters. And obviously, the Bayesian treatment will be more expensive, especially for neural networks. But once we have that, it will be very helpful. For example, it can produce uncertainty estimation, which is very important for reinforcement learning or active learning. And then the prediction can be more robust, specifically in the case for insufficient data and noise, and obviously the prediction will be also more accurate. And in order to have this efficient treatment, we're going to discuss later a efficient lightweight Bayesian treatment for general neural networks. And for it to be efficient, what we want is that the solution needs to be compatible with backpropagation, and it also needs to be sampling free during both training and testing, since sampling is typically inefficient. Last but not least, we want it to be intuitive and easy to implement. Unfortunately, no existing method can satisfy all three requirements. Therefore, we need to develop our own methods. And at that time, our idea is that instead of treating the weights and neurons as points, deterministic points in a high-dimensional space, we can treat the weights and neurons as distributions. And we should allow these distributions to be feed-forwarded and backpropagated through the networks. And since these distributions are parameterized by natural parameters, we call this model natural parameter networks. Just to give you slightly more details, in each layer of our natural parameter networks, or NPN, we first perform a linear transformations on the distributions, and then we're going to map the mean and variance of these distributions for its corresponding natural parameter. And then we're going to perform nonlinear transformation on the distributions parameterized by the natural parameters. And to verify the use of our output variance as uncertainty estimation, here we plot the error versus variance for each data point in a data set. We can see that larger variance typically indicates larger expected error, and also means that the model is less certain about the prediction. And this verifies the use of our variance as uncertainty estimation. And this is another example of MNIST. We can see the larger variance usually indicates lower accuracy. And so far, we have talked about different concrete models. we talk about the unified framework that subsumes all these models. And these models can actually be represented by a larger graphical models, and the Bayesian treatment of these models can be handled by our natural parameter networks. And interestingly, with a little bit of game theory, we can actually generalize these models from single domain reasoning to multi-domain adaptation. Specifically, for example, in medical application, the doctors may want to transfer model across patients of different ages, and here patients of different ages corresponds to different domains. And the age here is a continuous concept. Therefore, we call this problem continuously indexed domain adaptation. So essentially, typical and categorical domain adaptation tries to transfer between a handful of domains, but continuously indexed domain adaptation or SIDA tries to transfer from infinitely many domains to infinitely many target domains, where these domains follow some kind of trajectory. And to address this problem, we developed the first general method for continuously indexed domain adaptation or SIDA. And then here, the encoder will take in both the data and domain index U as the input to produce the corresponding embedding Z. And the predictor would take in the embedding Z to predict the labels. And for the discriminator, this is something really interesting happening, because instead of asking the discriminator to make classification, we're going to ask the discriminator to directly regress the domain index as a continuous value. And not only that, we're going to predict both the means and variance of the domain index. So you can see that correspondingly, we're going to use the negative Gaussian log likelihood as a loss function, and all of these components will be trained adversarially. And our theory shows that by doing this, our SIDA can match both the expectation and variance of the domain index across different domains. And interestingly, this SIDA model can actually be viewed as a Bayesian deep learning model as well. And specifically, the encoder can be treated as a deep component that extract encoding Z, and the predictor and discriminator can be thought of as a graphical component that model the predicted distribution and align the encoder Z distribution from different domains. And in terms of theoretical analysis, we can show that after SIDA converges, we can match the expectation and variance of the domain index across different domains. More importantly, we also show that the global optimal of the two-player game between the encoder and the discriminator actually matches the global optimal of the three-player game between the encoder, predictor, and discriminator. It basically says that you can train the encoder, predictor, and discriminator jointly and achieve both perfect alignment and accurate predictions together. And so far, we have assumed that this domain index is already known, but what if the domain index is unknown? And this would lead to another interesting extension of our methods that can infer the domain index from the data in an unsupervised learning manner. And to evaluate our methods, in real-world medical settings, we focus on the problem of sleep study at home. The input is just some time series signals coming from the patient's nasal cannula and breathing bells. So these are breathing signals. And then the predictor, for example, a neural network, will take in the signals and predict the corresponding sleep stage, which is one of the four classes: awake, REM sleep, deep sleep, and light sleep. And to evaluate our methods, we use three sleep study dataset. We use SHHSS, MESA, and SOF. Note that all of this dataset, they contain subjects of different ages, where age is a continuous domain index. And we propose to evaluate continuous domain adaptation with two settings: domain extrapolation and domain interpolation. For domain extrapolations, we're going to use younger patients, and we're going to use younger patients as source domains and elder patients as target domain. For domain interpolation, we're going to use younger patients and elder patients as source domain and middle-aged patients as target domain. And these are the results for different methods. We can see that typical categorical domain adaptation hardly improves the performance and may even hurt the performance. And SIDA, our method can improve the performance in both settings, and in particular, it has larger performance gain in the extrapolation setting since it's more challenging. And besides sleep staging, we can actually develop a similar model that takes in the breathing signal to detect and assess Parkinson's disease. So with all this work, what we have learned is that in the Bayesian deep learning framework, we can actually use graphical models to help formulate both the deep and graphical components. And this framework is suitable for any applications as long as it involves both deep representation learning and complex conditional causal dependencies. And the bottleneck layer representation can serve as a bridge to marry these two components. And last but not least, the tight two-way interaction between the deep and graphical component is crucial for information exchange and performance improvement. Besides Bayesian deep learning, we have done also other work, including spatial temporal learning, speech recognition, time series analysis, and bias and fairness. And in particular, one of our work, we developed the first convolutional LSTM or conv LSTM in computer vision and has now become a standard building block in the computer vision community and also in the AI for science community. And then it also becomes a standard building blocks in modern deep learning frameworks such as TensorFlow and PyTorch as well. So here we propose one of the first probabilistic framework that unifies deep learning and graphical models. And this framework has impacted the designs of a lot of models, and it has inspired hundreds of follow-up works from institutions like Google, Microsoft, CMU, and MIT. And particular, one of our work ended up being the most cited paper in KDD 2015. And one of the other work is the CVPR 2022 best paper finalist. In terms of industrial impact, a startup, Emerald Innovation, has taken our work in the healthcare domain and has become one of their fundamental components in the systems. And Microsoft NSN Weather has adopted our work for weather forecasting. And Amazon has deployed our methods in their recommended services as well. And just to conclude, here we propose a unified framework based on deep learning. And under this framework, we'll develop a concrete model, which happens to be the first hierarchical Bayesian model for interpreting multimodal LLMs. We developed the first Bayesian deep learning model to provide causal explanations for graph neural networks, and we also developed the first deep learning healthcare model for infinite in continuously indexed domains. We also developed an efficient lightweight Bayesian treatment for neural networks and Bayesian deep learning. Last but not least, I would like to thank all my students and collaborators and sponsors, without whom all this work would not have been possible. These are the related references, and with that, I'll be happy to take any questions. Thank you.
Thank you so much. Amazing talk, and really great to see all the impact this is already having and potentially will have in the future. If you have a question, just either drop them in the chat or just raise your hand and we will call you up and you can ask a question. And just because the question to me came earlier, this talk will be available on our YouTube channel as usual. So we will keep you updated via email about that. Any questions? Yes. Do you have a question, Yupei?
Yeah, I have a small question. Thank you. Firstly, thank you for your excellent sharing. I have learned a lot from your talk. And I'm curious about one small thing, how to define the number of concepts for data level, image level, or patch level.
Oh, that's a good question. Essentially, a hyperparameter, just like any topic models, it can be treated as a hyperparameter, or if you can have a non-parametric model, you can actually learn this number of topics on the fly. Yeah.
So is there any suggestion initial numbers, or you're just learning from start?
Oh, That's a good question. So when we are doing the experiments, there are several prior work that tries to get concept explanations, and we try to follow exactly their setting. So we choose a number of concepts to be 100. But when we did try different number of concepts, and we find that if it's relatively stable, but if the number of concepts is too small, then it might happen that one concept can contain multiple semantics, right? And if the concepts are the numbers are too large, then there might be a lot of redundant concepts. So basically, different concepts may actually mean the same thing. Yeah. So the number of concepts it's a important hyperparameter, definitely, but it also is relatively stable.
Okay, thank you so much. So is there
Okay.
any possibility to match the concept groups into some real explanations? Yeah, my field is the computational pathology, so I think
Ah,
pathology images also have such similar ideas with the concept and causal inference.
I see. So your question is that all of these methods is actually unsupervised, right? You discover the concept, but you don't know what each concept actually means.
Yeah, yeah.
In
So,
human
but
language, basically.
clinical settings, I think the explanation of the concept groups, like what kind of cells this concept means, such explanations are also important.
Yeah, I think it's a good question. I can answer it probably in two parts. First of all, it might be helpful if you can build on some at least part of the concept annotations. If you know concept bottleneck
Okay.
model, they actually have some annotation, and in some of the data set they have ground truth concept annotation. But you can also do it in a semi-supervised way, meaning that you can have some annotated concept, but you can also try to learn uh, new concepts, and you can try to connect the new concepts to the old concepts to see their connections. Then, and probably you're gonna have some insight. And and since you're working on computational pathology, we have some related work as well. We're collaborating with doctors. And my experience is that it would be better to directly have closer collaboration. And if you find something, it's actually a gold standard to ask them directly to see if they find something, right? And I think part of the um, amazing promise of this concept discovery is that sometimes they can discover something that's unknown to previous knowledge. And I think there is some previous work on discovering new subtypes of diseases, and probably also from computational pathology. And that's through collaboration with clinicians and doctors. Right? So maybe no label is a good thing. That means you're actually discovering something new.
Yeah, thank you so much for sharing. I have no more questions. Thank you.
Thank you. Thank you for your question.
Thank you very much. There's another question from SC. If you would like to ask directly, you can do that as well. Well, I'm also happy just to read it out. SC is asking, can the model/framework generate point estimates as well as statistical inference in a 95% confident interval for causal inference? For example, the association between built environment and certain health outcomes like mental health, rather than only point estimates like predictions.
Oh, that's a very nice question. I think part of our advantage of being Bayesian and probabilistic is that all of these variables that you're predicting, you're actually predicting a distribution, right? And this distribution naturally encodes both the most probable prediction and also the uncertainty estimation. And if you want to get 90, for example, if you want to get 95% confidence interval, you can use a distribution-based approach or distribution-free approach, right? Distribution-based approach means that you can assume the prediction has some distribution, for example, Gaussian distribution, and according to the Gaussian distribution, you can see where the 95% interval is, right, for exact Gaussian distribution. Right. And for distribution-free approach, you can produce some score, and perhaps you can use some kind of a conformal prediction to get your statistical hypothesis testing or confidence interval, that sort of stuff.
Okay. Thank you
Cool.
very much.
Thank you for your question.
Are there any more questions? If that's not the case, thank you very much, Professor, for speaking, and thank you very much for answering the questions.
Thank you for having me.
No worries. Thank you everyone for coming and listening to the talk. As I said, this will be available on YouTube soon, and there will be an email coming around, and there will be more seminars coming in the coming weeks. We have one next week. Markus Müller is coming to talk to us, and that will be a hybrid one, so it will be both in person and online. And then we have one on the 22nd as well. So look out for the emails, and there's more information to come. So thank you very much, Professor, for coming
Thank
today.
you. Thank you. Thank you for inviting me, and have a nice day. See you.
Thank you. Bye, everyone.
Recording